Properties of summations. So in this video, we're going to talk about the different properties that summations have. So say that we have a sum from n equal 1 to n, or I'm sorry, from I equal 1 to n of c. And so what this says is I'm going to add c a lot, over and over and over and over. Why is it the same thing over and over? Because my index here is I, but as you see here, there is no I in there. It's just the same constant over and over. So it's like I'm summing I equal 1 to, I don't know, let's say 3 of the number 4. So what does this mean? At I equal to 1, I put a 4 there. I equal to 2, I put a 4 there. I equal to 3, I put a 4 there. So I add 4 for I equal 1, 2, 1, 2, and 3 for the different I values. And I just add up those numbers, right? So another way to add 4 3 times is to say 4 times 3. So it's 3 times, so this ending sum and the top index here is multiplied by that constant 4 there, okay? So this c here, how many c's are there? There's n total. So I'm going to take the c, and to add all those c's up is the equivalent of multiplying n times c. Okay? Just like that example I gave with concrete numbers. Now, this next one here says the sum of AI plus or minus BI is equal to the sum of the AIs plus or minus the sum of the BIs. So the sum of the sum of sequences is equal to the sequence of the sums. So the sum of the sequent sums, right? So it's kind of a tongue twister right there going on. So my two sums here can be broken up over the plus and minuses, which kind of makes sense if I'm just adding like numbers like 1 plus 2, and then like the next one is like, I don't know, 3 plus 4, and then the next one is like 5 plus 6, and we just keep going on and on. I can group all these together as one sum, 1 plus 3 plus 5, and then I can add to that the others, 2, 4, and 6. I can have their own 2 plus 4 plus 6, right? So this is a sum, and this is a sum, and it's split up by that plus sign there, okay? So grouping them, we can group them together by separating the AIs and the BIs with the plus or minus, okay? So if there's a C here, right, if there's a C there, a constant, I can use the constant multiple rule and pull the C all the way out. And so this is like, say you had like, so the AIs were like 1, 2, 3, 4, right? And then the C was like 5. So I had 5 times 1 plus 5 times 2 plus 5 times 3 plus 5 times 4, right? What can I do? I can factor a 5 out of all of those, and then I have left this right here. And so what is that? That's my series right there, and then my constant multiple is factored out, okay? So I can factor out the C from each of those AI terms, and I get C times the sum from I equal 1 to n of AI. This one here says that if I start the sum at 1 and I go to k, and then I add starting from k plus 1, the term, this is the next term. So it's the next term after k is k plus 1. then I go to n. This is the same as adding starting at 1 and going to n. Okay, so the way to think about this is I sum up the first k terms here, and then I sum up the k plus 1 to the nth term there. Okay, so like if k was equal to 3, okay, then I have a sum I equal 1 to 3 of ai plus the sum of I equal, well, k plus 1. If k is 3, then k plus 1 is 4. 4 to whatever my n value is, okay, of ai. So it's literally, it's the first 3 terms here, and then the 4th term through the nth term for that second part. So that adds up from the first to the nth term, okay, combining. All right. So now here's a formula, and these are important formulas. You need to just write them down and have them in your repertoire. You probably don't need to memorize them. You just reference them when you need it. But when you're adding up, so this is different than anything that we've done so far here. This is specifically saying I equals 1, and I sum to n of I. Then this is equal to n times n plus 1 divided by 2. Okay, so what do you might be thinking like, Mr. Clark, I don't even understand what you're writing right now. Okay, so let's do something more concrete. So I equal 1 to 5, okay, of I. So what this says, my index I, okay, starts at 1. So when I equals 1, I plug in a 1. So I have 1 there. And this symbol here is summation, right? So that means that I add the next term. Well, what's the next term? When I equals 2, what do? I plug in a 2 everywhere I see an I. Well, there's just an I, so I'll plug in 2, right? And then I go to the next term. When I equals 3, I plug in 3. When I equals 4, I plug in 4. And the last one is when I equals 5. Remember, this is the last term. And when I equals 5, I plug in 5 for I. Okay? And so then I add those. 1 plus 2 plus 3 plus 4 plus 5. Let's see. Okay, n here, n was the top, so n is 5 for this particular one. So what would that be? That'd be 5 times 5 plus 1 over 2. So what is that? 5 plus 1, that's 6. So 5 times 6 over 2. So 30 divided by 2, that's 15. Does this make sense? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So that checks out. So the formula does work. How about that? So, interesting story. A long time ago, there was this famous mathematician. His name is Gauss, Frederick Gauss. Now, this dude, when he discovered this formula that I have written here, this guy was in elementary school, like 1st or 2nd grade. Kind of crazy, right? So the teacher apparently got really annoyed with Mr. Gauss because he was a very inquisitive, questioning everything, why does this work this way and all this stuff. And the teacher said, you're frustrating me. Here's what I want you to do to occupy your time for the next hour. I want you to take all the numbers between 1 and 100, and I want you to add them together and then tell me what that adds up to. And so she thought, great, this would be something that will take his time, and I'll have at least an hour to help the other students, and he'll be preoccupied with this, and it won't be bugging me. Well, unfortunately for her, he came back in about 30 seconds to a minute with the answer and said, here it is. And she was stunned and could not figure out how he was able to add up all of these numbers 1 through 100 and get the answer so quickly, okay? So once again, if I'm adding from 1 to 100, that last term is 100. So I do 100 times 101, and then I divide by 2. So how did Frederick Gauss do this as a first or second grader? Well, here's what he noticed, all right? If he took all of the numbers that he had, 1 through 100, and then he rewrote them again, just in the opposite direction, then what he saw was this. If he added this column here, he got 101. If he added 2 and 99, he got 101. If he added 3 and 98, he got 101. If he added 4 and 97, he got 101. And so on and so on and so on. And lo and behold, when you add all these up, well, guess what? How many of those pairs do you have? Well, how many numbers are there, right? There are actually 100 numbers. So how many times are you adding 101? Well, you're adding 101 100 times. So if you just multiply those two numbers together, then you get your answer of 10,100, okay? But what's the problem here? We added the 1 through 100 here, but we also added the 100 to 1 here. And so we added it double what we needed to. So to get rid of the double, I divide everything by 2, and I get back to my answer right here. So it was pretty clever how he came up with this little formula, you know, just as a 5, 6, or 7-year-old, okay? So pretty stinking cool, all right? Now, the next one is the sum of the squares. Now, the sum of the squares is a little different. If you had like I equal 1 to, I'll do 4 of I squared, what this says is I take 1 squared. The first one is I equal to 1, right? And so I take 1 squared, and then I add the next one, 2 squared, 3 squared, and the last one, 4 squared. And so what does this get me? It gives me 1 plus 4 plus 9 plus 16. So that's, I guess, 25, and that's 5. So it adds up to 30, okay? So this rule here is not quite as easy. So if n equals 4, then you end up getting 30. That's what we just showed. So the formula here for this one, which can be proved through a proof technique called induction, mathematical induction. If you want to look that up on YouTube, I'm sure you can find plenty of videos that show how to prove this formula through mathematical induction. Pretty cool. If you got spare time and you're kind of a geek like me and you just want to check it out, it might be cool to do that. So let's try it out with that n equal to 4. I had 4 times 4 plus 1 times 2 times 4 plus 1, all divided by 6. So that's what? 4 times 5 times 9 divided by 6. 3 and 6 cancel, and the 2 and the 2 cancel there. So that's going to get me 2 times 5 times 3. So that gets me 30. Okay? I know I wrote 3 there. Just ignore that. You know what I meant to say. Okay. So that's how the formulas work. One more, I cubed, in case you ever run into like a cubic. So these are useful. I promise you these are going to pop up when you're working through some of your problems potentially. So whenever it's a constant, you use this formula. When it's like an x, or I turn it into an I use that formula. And then I squared, I cubed. That way we can convert pretty easily, okay? So I cubed is interesting. It's literally I, except for you square it, okay? So kind of interesting how that works out. All right, so let me zoom out. That way you can see all of the formulas that you just need to reference. I'm not saying to memorize this stuff, just have it on a note card where you can easily access.